And maybe we could say we're all here. Is it good? Okay, well, I'd like to welcome Thomas Lamb from the University of Michigan, who will give our July talk on matroids and scattering amplitudes.
Yeah,
Take it
thank
away.
you. Thank you for the introduction and thank you for inviting me to speak. Uh, I had the feeling that the audience of this seminar likes things like matroids and hyperplane arrangement. I would be talking about some appearance of some relation between hyperplane arrangements and physics. And it's sort of loosely based upon these two papers, one with a title that's nearly the same as this talk, and one which is joint with Chris Eur. Um, yeah, so I'm gonna start with some physics, which and I think that's the part that's perhaps the least familiar with the audience here. I want to talk about some functions called scattering amplitudes. And the kind of physics that one should have in mind is that you have a bunch of particles, and then you're smashing them together inside a particle accelerator. Um, it could just be three particles, say two particles collide and one comes out, or maybe four particles, so two particles collide and then two come out, and they're different particles. Um, and what we want to do is to calculate the probability that you witness some particular event um, in space. And the sort of theoretical foundation of this is something called quantum field theory. And in a quantum field theory, you can calculate functions called amplitudes. So I'm just going to give a really rough sketch of how this works. So you give me, let's say, n particles, and you tell me the space-time momentum vectors of each of the particles. So these are four vectors, 3 + 1 space-time. So these pi live in um, so the physical case is the four-dimensional space. And I want to write down a function. A stands for amplitude. A depends on the momentum vectors. It also depends on other things that I'm going to hide. So it depends on what kind of particles I'm colliding. Also, it depends on some sort of internal features of these particles. It may have some other quantum numbers and polarization vectors. So I'm hiding all this there's more input into this function, but I'm just going to pretend it only depends on the momentum vectors. And if you want to know the probability that you witness this event happening in your experiment, what you basically do is you integrate the mod squared. So this is possibly a complex valued function. You integrate the mod squared of this thing, and then you divide by some normalization vector. You integrate this over the region that you put your apparatus. Okay, in any case, this is some function, some complex analytic function, let's say, that depends on inputs, which are uh, four vectors or d vectors if we're doing arbitrary space-time dimension. So I've got n four vectors, and we're going to make some assumptions. The vectors satisfy momentum conservation. Otherwise, it's just sort of zero function. So it's on the support of this, the vectors have to satisfy this. And we often make the assumption that to simplify things, it makes things mathematically simpler if we assume that the vectors are massless. What that means is that with respect to some inner product, which is the Lorentz inner product, the dot product of the vectors with itself will be zero. So, but it won't be important to us that we're doing 3 + 1. Like the signature of the inner product won't be important in what I say. Okay. So I'm using here some notation that's very common in physics, which is that if I take a vector and I square it, this means I take the vector and dot it with itself with respect to some inner product that's assumed to be fixed. Okay. So so the amplitude uh so by a physics sort of axiom, the whatever answer we're looking for is invariant under transformations of space-time that preserve the inner product. And so a basic theorem in invariant theory says that, so if this function is invariant under sort of rotations of space-time, then the function should be, you should be able to express it in terms of the dot products between the vectors. So that's the dot products will generate, so if you're looking for, let's say, polynomial functions of a bunch of vectors that's invariant under an inner product, then you take the invariants for the orthogonal group are generated by these inner products. The two is a historical thing. So I'm going to write the answer instead of writing the answer in terms of a 4 by n matrix or a d by n matrix, I'm going to write the answer in terms of the dot products, which are called Mandelstam invariants Sij. So now the task is to find this scattering amplitude, this function of Sij. Okay, so in the setting of perturbative quantum field theory, which is the theory behind how to calculate these functions A, the answer to this problem. So first of all, it depends on n. N is the number of particles. So that's sort of fixed. Once I've and I also fix other information such as what kind of particles I'm colliding and so on. This function an has a perturbative expansion, so it's got some kind of asymptotic expansion. Not mathematically proven to converge, but anyway, it's empirically very effective. It's got an expansion such that each piece of it is given in this form. It's a sum over some combinatorial things called Feynman diagrams. And each summand of the summation, so this summation is a finite summation over a bunch of Feynman diagrams. I'm going to give an example in a moment of what a Feynman diagram is. You're supposed to sum over some mathematical objects called Feynman diagrams. It's a finite summation. And then you take an integral. The integral is over L times D sort of Euclidean space. So L is the number of loops. So that's which term you are in the asymptotic expansion. That's also the first Betti number of these Feynman diagrams, which is a graph. And D is the dimension of space-time. And you integrate some kind of rational form. The rational form has which rational form you use, rational differential form you use in this integral depends on what kind of particles you're scattering. So the choice of quantum field theory. It also depends on the momentum vectors and so on. So all the other things are input into this. So this is just a rough form of it. But we're going to just focus on the first term in the asymptotic expansion today. And the first term, L is equal to 0. The Feynman diagrams are trees. So that has Betti number 0. And there's no integral here because it's, so it'll just be a rational function. So this first term in the perturbative expansion of the amplitude is a rational function of the Sij. And so that's the starting point of this. So these other guys are more complicated, but I won't talk about them today. So if you just talk about the first term, it's usually called tree amplitude. This is the jargon in physics. The tree amplitude is the first term, which is obtained by summing over just Feynman diagrams that are trees. So this kind of thing is what got Feynman famous in the 50s and 60s. So on. Okay. And the other thing I should say is that even though this is not mathematic, there's other ways to define this, but this is the way that's, like in practice, this is the way that we use to compare with experiment, and it's been super effective since the 60s. Like this is basically like the last 50 years, this is just what people crunch to compare with experiments in particle accelerators. Even though there isn't a proof, as far as I know of, that this thing equals another more conceptual definition of an amplitude. Okay. So just to give an example, so this is our basic example and the starting point of how to connect to matroids. Is something called the planar phi cubed amplitude. So these words up here, especially this phi cube thing, is a description of what kind of interactions are allowed between the particles. So if if I collide a bunch of protons together, I'll get a different kind of interaction compared to if I collide a bunch of photons together. So so the kind of particle I have in mind when I'm writing down this amplitude, they're called scalar particles. They're not very common in terms of the kind of interactions that we see. And in particular, this phi cubed amplitude says that the particles will only interact sort of 3 at a time. And it doesn't correspond to, as far as I know, it doesn't correspond to an actual particle. So this is a toy model that you will find in a textbook in quantum field theory. And in this case, the summation here is over cubic graphs. And the first term of the summation, the first term of the asymptotic expansion is a summation over cubic planar trees. Planar is just to make what I'm about to say for the rest of the talk a little bit easier. In principle, you should actually sum over non-planar ones as well. But there's a way to reduce to this case. So the finitely many summands are indexed by these things called cubic planar trees. So if there's n particles, then I'm going to look at a tree with n leaves, and all interior vertices will have degree 3. That's a cubic planar tree. So it's planarly embedded into the plane, and the leaves are ordered 1 up to n in some particular, let's say, clockwise fashion. Okay, so the number of these cubic planar trees is a Catalan number, so it's just Cn. So if n is 5, there are 5 of these trees, which I'll draw. There'll be an example later on. And then how do I write this rational function? The rational function is described as the following: you associate to every interior edge of your cubic planar tree, you associate to it a propagator x sub e. So e is an edge. I associate a propagator x sub e. X sub e is the square of the momentum traveling along the edge. So you imagine that your momenta, so let's say there's P4, P5 here. So that's the momentum of the particle traveling. So all the arrows are going in. So the momentum, there's a momentum P4 particle going like this, a momentum P5 particle going like this. So whatever's going along here, by momentum conservation, it's got momentum P4 plus P5 in this direction. And I take that momentum and I dot it with itself, and that's the x sub e. Because of momentum conservation, I could also have taken these momenta and come the other way. And so there's sort of 2 ways to write this in terms of the S's. Either I dot P1 plus P2 plus P3 with itself, or I dot P4 plus P5 with itself and get the simpler answer S45. Okay, so the definition of this phi cubed amplitude is it's this rational function in Sij's. The Sij satisfies some relations because of, well, here's one of the relations. Anyway, the Sij satisfies some relations. In any case, it's a rational function in the Sij's, and it's obtained by summing over all cubic planar trees gamma. Then you take the product over all internal edges. In this example, there's always, every such tree will have 2 edges. And then you do 1 over the propagator, 1 over xe. In my particular example here, I will get this product. So the squared momentum traveling along here is S45. The squared momentum traveling along here is S12. And there are 5 terms. So let me write that down. 5 terms. That's the Catalan number. Okay, so that's some rational function. Let me see if there are any questions up to this point. So this is an example of a tree amplitude. It is an example of the first term in the perturbative expansion of some particular particle scattering process. It's not a particle scattering process that's sort of corresponding to actual particles, but it is a very famous toy model. Okay, so in this talk, the main idea is that so I gave you the combinatorial definition of this rational function. There's another way to obtain this rational function, and it comes from studying the geometry of the moduli space of n points on P1. So I'll explain this in a moment. So it comes from the geometry of this M0n, which may be familiar with many of you. And this M0n is a special case of a hyperplane arrangement complement. So what I'm going to do is I'm going to take the calculation on M0n that gives this rational function and replace M0n by an arbitrary hyperplane arrangement complement. And then I'm going to notice that the answer is completely matroidal and only depends on the matroid. And this will give the generalization of phi-cubed amplitudes to matroids. Let me just say a little bit here that I said, oh, this thing doesn't, this rational function doesn't actually come up. It doesn't actually come up in nature per se. But actually, in some way, it sort of does, in the sense that it's some kind of limit of a string theory amplitude. And of course, string theory is very closely tied to the geometry of various moduli spaces M, Gn for various genus. Again, in string theory, you can look at genus 0, which is looking at M0n. So the fact that this particular amplitude arises out of M0n is actually a manifestation of the fact that this comes out of a quantum field theory that's a limit of the string theory. So when your strings turn into particles, it will give this thing. And string theory is considered like has behavior that is similar to actual particle scattering. Even though we don't know if string theory matches with nature, it does have the properties that's expected of typical particle scattering. Okay, so let me just go back to the point. This M05, why is it a hyperplane arrangement complement? So this is probably familiar to a lot of you. So what is this space? So I'm taking 5 real or complex points in one-dimensional projective space in the projective line, and they're not the same point. The Zi is not equal to Zj, and I'm modding out by PGL2. So one way you can factor out this action, you can gauge fix this action is by putting, let's say, 3 of the points at 0, 1, and infinity. So let's say if you put, let's say Z1, Z4, I think this is the one. So put this at 0, 1, infinity using PGL2. So PGL2 acts simply transitively on 3 tuples of distinct points in P1. So this will completely get rid of this mod PGL2. And now I just need to record where Z2 and Z3 go. So here I'm drawing a picture. Over here, I'm drawing a picture of Z2, Z3. So the X coordinate is Z2, the Y coordinate is Z3. And what are the conditions that I have? Z2 is not equal to Z3, that's this hyperplane. And then Z2 is not equal to Z1, which is 0. Z2 is not equal to 1, is also not equal to infinity. So that's an affine picture. And same thing with Z3. So I end up with all of these conditions, and I've drawn all of these conditions here. So Z2 not equal to 0, Z2 not equal to 1, Z3 not equal to 0, Z3 not equal to 1, Z2 not equal to Z3. So M05 is this picture. So I've drawn the real points here. But when I say M05, I typically mean the complex points. So the hyperplane arrangement complement, I will mean the complex points of this picture. You could also draw it in P2 rather than in affine space. And now I put back in the hyperplane at infinity, which is somewhere out here. There's out here really far, there's a hyperplane at infinity. If I put that in, I'll get 6 hyperplanes, and that's this picture I've got here. Okay. So as a projective hyperplane arrangement complement, it's the complement to the lines is what this M05 is. Okay, so in general, M0n is has dimension n minus 3. Okay, so let me go through some assumptions and notations of hyperplane arrangements. So I'm going to consider a projective hyperplane arrangement. So that's A. And I'm always going to assume that it's essential, so that it's got sort of enough hyperplanes in it. And the complement will be denoted U. So U is some open subset of projective space. It's also an open subset of affine space because of the essential condition. And so associated to this arrangement, I'll have a matroid M, and sometimes I'll also need the oriented matroid. So at least in the beginning, it's enough to just think about matroids. Later on, I'll assume that this is a real hyperplane arrangement. I'll use the oriented matroid. But for now, just the matroid will do. So the base set, the grand set of the matroid is the set of all of these hyperplanes. A. So there's so E. So if A is equal to a collection of hyperplanes HE, E inside some set, then capital E is the grand set of this matroid. In particular, the grand set includes the hyperplane at infinity. So amongst other things, one of the things that should be pretty familiar is the cohomology of the hyperplane arrangement complement, which is isomorphic to something called the Aulick-Solomon algebra. And this is a matroidal object. As a ring, this so I will think of this as an algebra over C. So I'm taking singular cohomology or de Rham cohomology with coefficients in C. And so this will be a C algebra. So as a C algebra, the isomorphism class of this only depends on the matroid of A. So the bar over here is I'm using something called the reduced or projective Aulick-Solomon algebra. So if you're familiar with this subtlety, in any case, this ring on the right-hand side here is some explicitly defined combinatorial object. And what are the generators of this ring, or similarly, what are the generators of this cohomology? So it's a result of Brieskorn and I guess Artin in the M0n case, that the cohomology of this, let's say the de Rham cohomology of this of U is generated by some particular one forms. It's these kinds of one form. So if I write down if I write a linear, if I take the linear function that cuts out a hyperplane called Fe, then you can take as generating one forms to be d log of these functions, but I put Fe over F0. So F0 is the sort of hyperplane at infinity. So each of the Fe's may not be a well-defined function, but Fe over F0 will be a well-defined rational function. And d log of these things will be will generate the cohomology, and they get sent to, this is my notation for something inside a inside an Aulick-Solomon algebra. So the Aulick-Solomon algebra has generators that are given by the grand set, and they're in degree 1. Let me just write down that sometimes I'll also write like E bar for the projective version of this. So in any case, the generating one forms are labeled by either you can think of the entire grand set or the entire grand set minus a particular one that's the hyperplane at infinity. Okay. So I want to move on to a variation of this theorem to this which is twisted cohomology. And twisted cohomology, I think, was very popular in the 80s, 90s, and thousands. And what I'm going to do is I'm going to take a particular degree one element, so a particular one form, and this one form will be a one form which is a linear combination of things that look like this. So the one form I'll denote by omega, and it's a sum over AE d log FE. So this is over the entire ground set. And to make this well-defined projectively, I assume that the sum of the coefficients is 0. So yeah, I mean, one reason is, yeah, let me just write. So it's actually very common to define a potential, which is like product over E, FE to the AE, to define a potential function on this hyperplane arrangement complement. And for this to be sort of projectively well-defined, you will need this condition. And I'm taking d log of this. And that's my omega. So this you may have, instead of seeing the one form, you might have seen this potential function or master function in other contexts, or also likelihood function in some contexts. So using this one form, I'll define a rank 1 connection given by this differential operator. So it's a connection on the rank 1 trivial bundle where the differential, usually I take the normal usual differential and I sort of add a correction term to it. And I can take the cohomology with respect to this. I can take the cohomology of this connection in the sense of algebraic de Rham cohomology, for example. So what we do to calculate this cohomology is we do the same calculation as you would for algebraic de Rham cohomology, but you replace the usual de Rham differential by this differential. And that would define some cohomology group that looks like this. So I'm not going to go into the definition of this. But it's some twisting of the usual de Rham cohomology. There's sort of a variant, so something that's similar to the. So this is I guess a special case of the Riemann-Hilbert correspondence, which is to say that this, or you could think of this as a twisted version of the de Rham theorem, is that there's some de Rham thing and there's also a singular cohomology description of this. So there's over here on the right-hand side here is some topological object. Yes, you can also describe this cohomology group as some singular cohomology group with coefficients in a rank 1 local system. And rank 1 local systems on this space U is determined up to isomorphism by a representation of pi 1. So I take pi 1 of the space and I map into GL. Since it's a rank 1 thing, I map into GL1. So up to conjugacy, this rank 1 local system will determine, this representation will determine the local system up to isomorphism. And what is this? What is the L sub A here? So what is the local system? What is the representation that comes out of this local system under this isomorphism? It's described by the following thing. So you have some base point, and you take the loop that, if you take the element of pi 1, that's, you walk up next to a hyperplane and you go once around the hyperplane. I think my conventions are anti-clockwise. But anyway, you go once around the hyperplane, then this loop gets sent to this number in C star.
Thomas, we're assuming the AIs are not integers or something like that.
Let's assume the AI are not integers. Yeah, I have a stronger assumption. Yeah, sorry, there's a while before. There's still 2 slides before I get there. But I actually need an assumption stronger than that. Let's assume here, let's say, okay. So I'll actually need so generic A's will work for what I'm doing. But there'll be a more precise condition later on. Okay, so here I just talked about cohomology with coefficients in a local system. There are actually 4 cohomology or homology groups that are sort of relevant to take here. Uh, so there's you could take instead of cohomology, you could take homology with coefficients in this local system. Instead of cohomology, you can take compactly supported cohomology, and instead of homology, you could take locally finite homology. So this is also called Borel-Moore. So it has the same relationship to homology as compactly supported has to cohomology. And there's some natural dualities between these homology and cohomology groups. So homology is due to cohomology. Locally finite homology is due to compactly supported cohomology. So compactly supported, that means you only allow forms that are compactly supported. Locally finite homology is you allow chains that go off to infinity, but in a locally finite way. So you don't concentrate in any point of your space, but you do allow sort of infinite sums of chains, infinite sums of, yeah, one chains. So homology and cohomology are dual, but you have to take your local system and switch it to the dual one when you do this. Okay. So I'm going to assume, so this is to answer Graham's question. So I'm going to assume the following condition, which is that, for every connected flat of the matroid F, if I sum all the AEs for all the E's contained inside that flat, I should not get an integer. Yeah. Sorry, back over here, I should have said this is not an integer. But that's, so I actually want a stronger condition that is, you could do this for all flats and that's okay. Or you could just take any sum of these AEs is not an integer, that's also okay. Or you could just say the generic and that's okay as well. So I'll just assume this for the rest of the talk. There are things to say when it doesn't hold, but this will simplify things a lot. Under this assumption, a theorem of Kono says that there's some very nice homology and cohomology vanishing theorems. So the vanishing theorem says that under this assumption, which is sort of opposite to the usual cohomology assumption, there's only one non-vanishing cohomology group. And also you have the natural homomorphisms from homology to locally finite homology and from compactly supported to usual cohomology. These isomorphisms are, sorry, these maps are isomorphisms. So, so the map from homology to locally finite is if I have a one chain or a D chain, I can think of it as a locally finite D chain. If I have a compactly supported differential form, it is also a differential form. So that induces the natural map. And but these natural maps induce isomorphisms, and that's this theorem under this assumption. So I just want to say that if you don't have this assumption, for example, if you chose all the A's to be 0, if you chose all the A's to be 0, you're back to usual cohomology. So you're back to this result. And it's definitely not true here. So if all the A's are 0, then you're thinking about this cohomology group. And this thing definitely has a lot of interesting cohomology groups. It's not concentrated in one degree. So what you need to do is you take a very non-trivial local system and sort of maximally non-trivial local system, and then you will have this vanishing, you will have this vanishing theorem. Okay, so so the only so D is the dimension of the projective space that we're thinking about. So using this theorem of Kono, we can define these intersection forms on these twisted cohomology groups, and the definition is given here. There's more than there's a bunch of different variants, but let's say we do the the variant that is for a locally finite homology, then what I do is I take two locally finite cocycles, not cocycles, cycles, and I want to pair them. What I do is I take one of them, and I apply this isomorphism in the theorem here. So the isomorphism in the theorem gives me a map back, which is called regularization. So I take one of my locally finite chains and I keep it the same. And my other locally finite chain, I actually make it finite by using Kono's theorem. I change it to a finite one. And now I can just pair them in the usual way. So I just take the intersection product. Intersection product is this Poincare-Verdier duality. Alternatively, you can think in cohomology. I take some differential form here, some differential form here, and I applied this theorem backwards. So I take my differential form and I replace it by a cohomologous compactly supported form. And once I get a compactly supported form, I can now integrate. So what is this map here? This Poincare-Verdier map here is I just take my two forms. I take integral over the whole space of the two forms wedged together. Let's call them like theta wedge tau. So after I apply this map, one of them, let's say tau is now a compactly supported form, a D form. Theta is a D form. When I wedge them together, I'll get a compactly supported 2D form, and I can integrate over this 2D dimensional real space. And that's this map, up to some 2 pi i's. This, put it over here. That's what's going over here. So so it's crucial that I do this regularization first, because in general, this integral will not converge. If I have an arbitrary differential form here, a 2D form, it won't necessarily converge. Okay, so this defines things called Dirac intersection forms. I'm going to clean this up. So that's the definition, and this is kind of the main thing I want from the hyperplane arrangement perspective. This is the main technical thing that I want to talk about. But I want to clean it up a little bit so that it's a little bit more combinatorial. So recall that we have this Euler-Solomon algebra, which is called A dot, which is just, it's isomorphic to the cohomology for the with the trivial local system. And I also have this one form omega. I'm going to make a complex out of the Euler-Solomon algebra by just wedging with this one form. And it's a complex. If I wedge twice with this one form by skew symmetry, it'll be 0. So I get this complex, and this theorem, I think is it early 90s, is the theorem is an sort of the twisted analog of this Euler-Solomon algebra theorem. So this theorem, the Brieskorn Euler-Solomon algebra theorem, this theorem has a twisted analog, and the twisted analog is here. So there's a version that's just about complexes. Let me just state the version about cohomology groups. So it says that the twisted cohomologies are isomorphic to the cohomologies of this complex. And the omega is the same omega. So the omega depends on some parameters A. Those A's are going into my local system or into my connection. I'm using the same omegas here inside my Euler-Solomon algebra. And because of this cohomology vanishing, so I'm still assuming this genericity. Only one of the cohomology groups is non-vanishing, and that's this. I'll just call it A bar M comma omega. So that's the cohomology of this complex. I think this is sometimes called Aomoto complex, and sometimes this is called cohomology of an Euler-Solomon algebra. So this omega is an element, so it's in the degree 1 of the Euler-Solomon algebra. And the cohomology of this complex is invariant under changing the parameter, changing the omega to negative. So the image and kernel of this map doesn't change if you replace omega by negative omega. Replacing omega by negative omega is the same as changing A to negative A, which is the same as changing the monodromy to the inverse. So these monodromy, they'll go to the inverse number here, which is the same as replacing the local system by the dual local system, or the connection by the dual connection. So the point of this remark is that actually here there's this slightly it seems slightly complicated thing that I'm working with two different local systems, but actually the dual local system, when I present it in this combinatorial way in terms of cohomology and Euler-Extolman algebra, it's the same cohomology. There's the same cohomology. So this intersection form, well, this one in particular, this intersection form is actually a bilinear form on some particular vector space. So I instead of having two vector spaces, I just have one vector space now. And that's a technical, it just makes the problem a lot cleaner. So now my bilinear form is now defined on just on this space. So I have input two things which are both cohomology of the same Euler-Extolman algebra with respect to the same omega. And I'm trying to pair them together, and I'm supposed to get a complex number. This is assuming that the A's are given, the A's are also complex numbers. It turns out, so something that's not obvious, it turns out that this is a symmetric bilinear form. That's kind of not, sort of very non-obvious back over here. So because over here, there's asymmetry in two different ways. One of them is that the local system is, one of them I took the local system, the other one I took the dual. And the other thing is when I did the regularization, I applied it to one of them and not the other one. But actually, in the end, when you calculate what this is, which is what the theorem is about to say, this thing is a symmetric bilinear form. Symmetric bilinear and also non-degenerate. So from non-degenerate because of Poincare duality is a perfect pairing. Okay. So the theorem first of all is the advertised thing, which is that this pairing on this vector space, it doesn't depend on the hyperplane arrangement. Actually just depends on the matroid. So that's sort of theorem one. And in particular, this bilinear form with all the same properties, you can define this bilinear form for any matroid, even when the hyperplane arrangement, even when it's not realizable. There's such a bilinear form, and it's symmetric bilinear non-degenerate. The way you see that it's matroidal is actually you write down a formula for it, which I will tell you in a moment. There's sort of multiple good ways to write it. But let's just say there is a combinatorial formula for this bilinear form. To connect back to the physics, this in the case when I calculate this bilinear form, in the special case of this hyperplane arrangement complement M0n, you will get the rational function that I started with in the beginning. The rational function that's the sum over all cubic planar trees. You recover this where the s's, which are these, the a's will be equal to these s's before. So back in the beginning, I said, the amplitude is a function of these Sij's, which are dot products of momentum vectors. What I will end up doing is there's an A sub E associated to each hyperplane here. I'm going to set this will actually equal one of the Sij's. Each one will equal to an Sij. Okay. But to calculate this thing, you need to input something into a bilinear form. You actually have to put an element of this thing, or an element something that's in the top part of the Euler-Solomon algebra, you've got to input this in. So you can think of this as a top log form. You're going to put this into the bilinear form, and it's going to output some number. And so you actually have to put in a special thing. It has a name in physics. It's called a Park-Taylor form. So the definition, that's the title of this talk, is that and what's the definition of a matroid amplitude? The definition of a matroid amplitude is I'm going to take a particular differential form, which is a particular element in the top degree part of the Euler-Solomon algebra. I'm going to plug this into the bilinear form, and out will pop some complex number. But actually, this complex number is a rational function in the A's. So out will pop a rational function in the A's. So this will equal, let's use a different color, like this. This will equal some rational in AE. And that will be and this rational function would depend on my inputs. And what inputs will I use? I'll use something called canonical form of a tope of an oriented matroid. And that will be the sort of correct analog of this choice here. So this is the construction of this thing is in my paper with Chris Eur. So let me mention a few. So I'm going to sort of expand on all of these in this special case so that to explain it. But let me say a few other features of this. So the DRAM version of this intersection form is one of the variants of a form studied by Sheckman and Vachenko maybe 30 years ago, they called it a contravariant form. But the Betty version of this, the one so there were multiple versions of it. It turns out that the information in here and in here are actually not the same. The Betty version of this contravariant form is not quite something called Vachenko bilinear form. It's the inverse of the Vachenko bilinear form. So Vachenko bilinear form is like polynomial valued, but this thing is rational function valued. And that's what pops out of this calculation. The DRAM version of this intersection form. Oh, so I didn't say that much about this. So this thing, it's not a bilinear form on the Euler-Solomon algebra. It's some other kind of gadget. It's a bilinear form on the vector space spanned by topes, roughly speaking. So I won't get to talk that much about it. It's somehow more complicated than it has kind of more information. It's more complicated than this one. So this thing, it can be calculated using something that's in physics called scattering correspondence, in algebraic statistics called likelihood correspondence, and it's also called critical point equations by Vachenko maybe around 30 years ago. There's one way to calculate this form by summing over critical points. I'm going to try to explain what the combinatorics of this is. But I won't talk about, there's a way that I kind of really like, which involves a Bergman fan, but I decided in this talk, I'm going to skip the definition of the Bergman fan. So basically the first one is related to taking Laplace transform of certain subfans of the Bergman fan. And the second one is related to taking discrete Laplace transforms of various subfans of the Bergman fan. So if you like the language of sort of tropical geometry, then you might prefer this version of this. But I'm not going to give this version. So I'm going to come back to so these are all asides. I won't actually get to tell you much about the theorem. So I want to come back to so I've got a bilinear form on a vector space, and I want to evaluate I want to evaluate by plugging in some special elements in this vector space. So which one should I have? These ones are called canonical forms of topes. And this canonical form is motivated by some notion called positive geometry. So positive geometries are sort of semi-algebraic geometries. So examples of positive geometries are things like polytopes. They're positive parts of things like moduli spaces, toric varieties, or flag varieties. So if you take a toric variety, inside it sits a copy of the polytope. That thing is not actually a polytope because it's embedded in a curved way in the toric variety. Another example of a positive geometry is you take a flag variety or Grassmannia, and there's something called a totally positive part of it. That's a positive geometry. Or you could take a moduli space like M0n, take the one connected component of the real points and take the closure. That's another example of a positive geometry. So positive geometries, by definition, have a rational top form associated to it, and that top form is called a canonical form, and that canonical form is the input to this procedure. Is the input that I'm going to plug into this bilinear form. In the case of a hyperplane arrangement complement, what I'm going to do is I'm going to take one of the regions in the hyperplane arrangement complement, and the positive geometry is the closure of that. It comes with a differential form called its canonical form, and it will be the input. Chris Eur and I realized that you can generalize this notion to any oriented matroid. And so I'm going to write down, and this will be kind of possibly too much to absorb in the sort of 2 minutes I'm going to say it. So what's the theorem? The theorem is for each tope P of my oriented matroid, there's a distinguished element called the canonical form of the tope. It lives in the top part of the Euler-Solomon algebra, and it's uniquely defined. So it's called the canonical form of the tope, and it's uniquely defined by a recursion. The recursion is if you take the residue, so for each element in the ground set of the matroid, there's a residue map from the Euler-Solomon algebra to the Euler-Solomon algebra of the contraction. And it reduces the degree by 1, which is what you expect a residue to do. I kind of wrote down the definition of this residue, but it's probably too hard to understand like that. So it extracts one of the generator. If your wedge contains the particular element that you're taking residue with, then you just get rid of it, and up to sign you get rid of it. If it doesn't contain that thing, you just send it to 0. That's what this residue map does. So for each tope P, once you found this canonical form, it satisfies this nice recursion, such that when you take the residue, you will get the canonical form of a smaller tope in the contracted matroid. So for example, if I take the tope P here, I'm drawing hyperplane arrangement complement. So I take the tope P, and I want to take its residue of its canonical form along E, then what I'm going to get is I'm going to get the canonical form of Q, and Q is this tope in the contraction. And then there's when you're down to dimension 1, when you're down to rank 1, there's some it's just plus or minus 1. The canonical form is just plus or minus 1, depending on some choice of chirotope. Okay. So yeah, so quick summary is that for each tope, there's some distinguished element in the Euler-Solomon algebra satisfying a huge number of recursions. And it has sort of lots of remarkable properties. It's possible to use these things to get a basis of the Euler-Solomon algebra. You can even get rid of this, like it actually gives you a basis of the whole thing. But this here, I'm just saying the top part. And sort of this, if you're familiar with sort of the bijective version of the dimension of the top part of the Euler-Solomon algebra, it's the dimension of this thing is equal to the number of bounded regions bounded with respect to a generic extension of your of your hyperplane arrangement. So that's one of the theorems of, I guess, Green-Saslavsky. So it turns out that these canonical forms, a different construction of them, not this recursion, was known to Yoshinaga. So around, I think, this is a paper from around 10 years ago. Okay, so I'm kind of rapidly running out of time. So I want to tell you what the combinatorial formula for the bilinear form evaluated on the canonical form of a tope is. And it's formulated in terms of the lattice of flats. So L of M is the lattice of flats of the matroid. Flags M is I'm taking full, so saturated flags of flats. And to a saturated flag of flats, I'm going to associate this this rational function, which is given by this formula. So it's it's one over a product of a bunch of linear things. And the theorem is that when I pair two canonical forms, I will get a sum over flags that are kind of compatible with both topes. So I'm going to give the example only in the case where I pair a tope with itself. And so I'd like to explain it in the case of this the case M0n, the configuration space case. So in this case, the matroid is a complete graphic matroid on n-1 element. So if n is equal to 5, as it is in my picture, n is equal to 5, then I'm taking the graphic matroid on K4, which will have a ground set with 6 elements. The 6 elements are the 5 hyperplanes in this picture together with the hyperplane at infinity. And the A's will be the A's. I've now labeled the hyperplanes with the correct A. So this is, so A of this hyperplane is S12, A of this hyperplane is S24, and my tope is this P. So this is going to be my input data to the problem. And what I have to do, so here's my P. So here's my P. Oh, that's not a very good color. Here's my P, and I want to look at basically flags of flats that are on the boundary of this P, of this tope. So one kind of thing that you can do is you can take a facet of this tope, so an edge. So I could take, for example, this facet of the tope, and then I take this vertex that's contained inside the facet. So that's one possible flag that you can take. And this flag, the one that I just drew, gives it corresponds to this term in my formula. So I have the facet here. I have a linear factor correspond to the facet, and then I have a linear factor corresponding to this vertex. The vertex is the vertex is the flat that contains 2 elements, which is this hyperplane and this hyperplane. So that gives this linear factor. It turns out that there are 6 such flags. So the answer is the sum of 6 things. So these the flags over here are slightly more interesting because so for example, the flag here, the flag here will correspond to this term. So it's the hyperplane S23 and the vertex S234. S234 is the linear function that is a sum of 3 things, not just 2 things. But actually, by momentum conservation, this sum of 3 things is equal to actually just 1 thing, if I rewrote it. So the formula gives me 6 terms, but it's actually equal to the 5 terms that I had in the start of the talk, which is this phi cubed amplitude, the sum over Catalan many cubic planar trees. So the combinatorial formula for this bilinear form gives me 6 terms, but the Feynman diagram formula gives me 5 terms. So this brings me back to the beginning. So the summary is that these scattering amplitudes in physics in this special case of M0n is related to twisted cohomology of hyperplane arrangement complements, and that allows us to define define amplitudes, these interesting rational functions, amplitudes for matroids, for arbitrary matroids, and I think there'll be interesting things to study. Okay, thank you.
Thanks, Thomas. Are there any questions?